So in this video we are going to discuss the question in the thermal and statistical physics that appeared in JRF June 2016 examination. Okay, so let's continue with first question. So the statement is, a box of volume V containing n molecules of an ideal gas is divided by a wall with the hole into two compartments. Okay, so we are having a box whose total volume is V. Okay, and this is divided into two parts by a wall having a hole. So assuming this is a hole here in the wall, if the volume of the smaller compartment is V by 3, let's assume that here this is a smaller compartment whose volume is V by 3, and therefore the volume of the other compartment will be V minus V by 3. Okay, so that is equal to 2/3 of volume. Okay, such that the total volume, or if we call this is equal to V1 and this is equal to V2. Okay, so that V1 plus V2, that is equal to the total volume of the box. Okay, now we have to find the variance of the number of particles in it. Okay, so for that we first need to determine the probability. So here the probability that the gas molecule will be in the any one of the one of the part of the this box whose volume is B. So the probability of finding a gas molecule here in the sub part whose volume is B by 3 is given by let's call that as P. Okay, so P is equal to the volume of the part divided by the total available volume. Okay, so that P, it comes out to equal to 1 by 3. So similarly Q, that is equal to the available volume of the this box divided by the total volume, and that is equal to 2 by 3 here. Okay, so now as we have learned in the random walk in one dimension. Okay, so this problem can be treated in a similar manner. So sigma n1 square that was equal to n p q, that's a variance in the number of particles. Okay, so here n is given, n is the total number of particles, and then multiply it by p, which is 1 by 3, and q, which is 2 by 3. So this is equal to 2n by 9. Here I want to make a remark here. The choice of P and Q, it doesn't matter here. We can take the probability of finding a gas molecule here in this compartment as the P also. Okay, it doesn't matter in simple words. So therefore the variance in the number of particles is 2n by 9. So hence V is the correct option here. V is correct. So let's continue with the next question. Next question is the specific heat per molecule. So we have to find the specific heat per molecule of a gas of diatomic molecule at high temperature. Okay, so please note that the word high temperature is really important to determine the degrees of freedom of the gas molecule. Okay, so let's try to understand this problem. So we are given a diatomic gas molecule. Diatomic gas molecule. Okay, so if you just take a look at how many the translation degrees of freedom a diatomic gas molecule is having, if I denote them as Ft. So a diatomic gas molecule will have 3 degrees of freedom. Okay, so degrees of freedom. Okay, see these are the translational. Okay, and how many rotational degrees of freedom? F, if I denote them as Fr, so 2 rotational degrees of freedom. So we can just take a look at the molecule. Suppose the molecule is placed something like this here. Okay, and let's call these as X, Y, and Z axis. Okay, so the rotational degrees of freedom, it's because of, if it's the molecule can rotate like something like this, or it can rotate along the something like this. Okay, but when it's rotating in its around its own axis, okay, so the degrees of freedom along this axis, it doesn't come into picture, because the point is that here the moment of inertia is quite small, and the corresponding energy which is required to which is required to activate this modes of vibration, that's quite large, and that's why we usually take only 2 rotational degrees of freedom. But now it's given that it's quite high temperature, so that means we can also consider the bivibrational degrees of freedom here. Okay, so bivibrational degrees of freedom, basically they arise for the diatomic gas molecule. So when these two atoms they are vibrating, either they can move like this, or they can move like this. Both atoms, either they will approach each other, or they are moving apart from each other. So this process leads to two different energy terms. One is the kinetic energy, and another is the potential energy of the interaction between these two gas molecules. Okay, so the kinetic energy term, it will give rise to a squared energy term, and the potential energy term, it will again give a squared energy term, in terms of intermolecular displacement. Okay, in terms of delta x, let's say. Okay, so therefore the bivibrational motion will give rise to 2 degrees of freedom. Please remember that in a few books it's the bivibrational degrees of freedom, which consist of these two terms, it is treated as one single degree of freedom. But when you consider the contribution to the average energy, then we take it equal to kVt. Okay, so please don't confuse it with that notation also. Rotational, I'm writing here FV as 2, where 1 degrees of freedom corresponds to kinetic energy term, and another degrees of freedom correspond to the potential energy term. So therefore F total is equal to 7, and the average energy per molecule will be the degrees of freedom multiplied by the average contribution from each degree of freedom. Okay, so that is equal to 7 by 2 kVt. Okay, or that is equal to 3 by 5 kVt. So now the contribution to the heat capacity, that is equal to dE by dt at constant volume, and that is nothing but 3.5 kV. So therefore here V is correct option. Let's take a look at the next problem. So it is basically related to the adiabatic expansion of a gas. Okay, so the statement is, when an ideal monatomic gas is expanded adiabatically from an initial volume V0 to 3V0, okay, its temperature changes from T0 to T. Then the ratio T by T0 is, okay, so let's try to solve this problem. So we are given a situation, we are given a situation of an adiabatic expansion of a gas. Adiabatic expansion of gas with the following condition, where volume changes from initial volume V0 to 3V0, and the temperature changes from T0 to T, and what we have to determine is T divided by T0. So we know that for an adiabatic process, because here it's the volume, the relationship between the volume and temperature that we really need here to solve this problem. Okay, so we know that for an adiabatic process, this relationship is known to us. This the PV power gamma, that is equal to constant. It's valid, okay, when the adiabatic expansion is taking place. Okay, because the gas is given to be a ideal monatomic gas. Okay, so that means the gas is bound to satisfy the ideal gas equation, which is PV is equal to nRT. Okay, now here P is equal to nRT divided by B. So when we substitute this P is equal to nRT by B here, so what we obtain is nRT by B power gamma, that is equal to constant, and this gives us, because n is constant, r is constant, and then the remaining variables, they are connected with each other through a relationship t b power gamma minus 1, that is going to be constant in an adiabatic process. So this is another relationship that describes an adiabatic process. Okay, so now because here the variables which are given to us, they are temperature and volume, so that means we will make use of equation 2 here. So that means for these two different conditions, so I'm going to write these two different conditions for the adiabatic expansion of the gas. Okay, so for the initial stage, I can write it's the temperature is T naught and the volume is V naught. So T naught V naught power gamma minus 1, that is equal to the final temperature, which is T, and the final volume, which is 3 V naught power gamma minus 1. Okay, so from here we can determine the ratio T divided by T naught. Okay, you have to just settle the variables. Okay, that is equal to V naught divided by 3 V naught power gamma minus 1, or that is equal to 1 by 3 power gamma minus 1. But now we are not yet at the final answer, so let me call this as result 3, equation 3. Now we are given a monatomic gas. Okay, so for the monatomic gas, we know that the translation degrees of freedom, that they are 3, and there is no rotational degrees of freedom, 0, and we need not to consider the vibration degrees of freedom also. Okay, because it's a monatomic. Okay, so therefore the average energy for this case is 3 by 2 R per mole. Okay, or per okay, or even we can here mean take the per molecule also. Okay, E and R T, sorry, there will be T also. So Cb, from here Cb will be 3 by 2 R, and then from the relationship Cp minus Cb, that is equal to Nr. Okay, and when we are taking n is equal to 1, so n will not come into picture here. So this implies Cp, that is equal to Cb plus R, so that is 5 by 2 R. Okay, so that means Cp by Cb, which is gamma, which we require here, that is equal to 5 by 3. So when we substitute here 5 by 3, okay, so this is equal to 5 by 3 minus 1, so that will give us 5 minus 3, 2 by 3 basically. So gamma minus 1 is 2 by 3. So therefore T by T naught, T upon T naught, that is equal to 1 by 3. When we substitute gamma is equal to 5 by 3 here, we obtain it is 2 by 3. So therefore here V is the correct option. So let's take a look at the next problem. We are given the internal energy ET of a system at fixed volume is found to depend on the temperature T as ET is equal to, so let me write the given equation ET, that is equal to A T square plus B T4. Okay, let me call this equation as equation 1. So now the entropy ST as a function of temperature is, so we have to find the relationship between entropy and the temperature. Okay, so here we will make use of the first law of thermodynamics, which says that the first law implies du, that is equal to dq minus dw. Okay, because the process is occurring at constant volume, so that means here dw term will disappear. Dw is pdv basically. Okay, so at fixed volume, so this term will become 0. Okay, so that means we are simply left with situation where we can equate the change in internal energy with the heat change involved, which by making use of the second law of thermodynamics, which is equal to TdS. Okay, so here the TdS is equal to, so that means TdS is equal to 280 plus 4b T cube multiplied by dt. So we have replaced this du with this term. okay, et dt basically. Okay, so from this equation what we can do is we can determine the entropy change, and that is equal to ds, that is equal to this expression divided by t. Okay, so we will obtain ds is equal to 2a plus 4b t square plus 4b t square dt. Okay, so then after integration we obtain S final or delta S, that is equal to S final minus S initial, and that is equal to, so after integration, so here we will have a factor of t again, so 280 plus 4 by 3 bt cube plus some constant of integration. Okay, so this can be rewritten as S final, that is equal to 280 plus 4 by 3 bt cube plus c plus si. So we can call this as another constant. So in general I can write this result as 280 plus 4 by 3 bt cube plus, let's say, another constant of integration where these two constants they are absorbed in C1 here. Okay, so in principle we should have some constant of integration, some constant along with this result, but since in all of these four options, so it's not there, so therefore the more appropriate result here is C. So C is correct option here. So entropy as a function of temperature is given by expression C. So let's continue with the next problem. The statement is, a gas of non-relativistic classical particles in one dimension is subjected to a potential Vx is equal to alpha mod x, where alpha is a constant. The partition function in terms of beta is given by, so let's try to obtain the expression for the partition function. Okay, because it's given that it's a system of non-relativistic classical particles. Okay, so therefore the corresponding Hamiltonian for the system is given by H, that is equal to p square upon 2m plus alpha x or Vx, the given potential. Okay, or that is equal to p square by 2m plus alpha mod x. Okay, let's call this as equation 1. So now note that here p square, because it's a one dimensional motion, so p square it's simply px square. Okay, so now the partition function in one dimension, that is given by q1 as a function of t and v, that is equal to 1 by h, and then the integral from minus infinity to infinity, the second integral from minus infinity to infinity, exponential minus beta, the Hamiltonian. Okay, so then I will substitute the Hamiltonian directly, so which is p square by 2m plus alpha mod x, and then the variables dx dp. Okay, now this is further equal to 1 by h minus infinity to infinity exponential minus beta p square by 2m dp, and the integral over the space coordinate, which is so I'm splitting it because of the alpha mod x, so it's 2 times 0 to infinity exponential minus alpha beta mod x dx. Okay, so this is further equal to 1 by h into its exponential minus alpha x square. Okay, so exponential minus alpha x square, the integral. So here I'm going to make use of the one of the result standard integral, which is minus infinity to infinity exponential minus alpha x square dx, where alpha is a constant and x is a variable, that is equal to under root pi by alpha. So here in this integral, the alpha is its beta by 2m, okay, or 1 by 2m kt. So therefore its value is under root pi by alpha, that will give us 1 by h 2 pi m kbt under root, that's under root pi by alpha, and then 2 times its integral, the exponential minus alpha beta mod x, okay. So its integral is exponential minus alpha beta mod x upon minus alpha beta, and the limits are 0 to infinity, okay. So exponential minus alpha beta infinity, that will vanish, okay, and exponential, the lower limit will give a factor of e power 0, minus lower limit, that will give a minus 1. So this minus 1 and minus this minus sign, that will give ultimately a positive sign. So after this simplification, we obtained Q1 TV is equal to 2 upon alpha beta h into 2 pi m. So in terms of beta, I am writing in terms of beta 2 pi m. It's 2 pi m kt, so it will become 2 pi m upon beta power 1 by 2, okay. And this is further equal to, after clubbing all the terms, 8 pi m upon alpha square beta square h square power 1 by 2, okay. So that is the answer, Q1 TV, that is equal to, so that is the partition function. Please note that here it's a typing error here. Actually here it should be C is the correct option here, but this should be read as 8 pi m upon beta square alpha square h square, and not as h cut square. So while doing typing, so it's unfortunately written as h cut square. So therefore C is correct here. So let's take a look at the next problem. The statement is, the internal energy ET of a system at fixed volume is found to depend upon temperature T as ET is equal to, so we are given the dependence of the internal energy on temperature as A T square plus B T4, okay. So then the entropy ST as a function of temperature is, okay. So in order to solve this problem, we will make use of the first law of thermodynamics, which says that the first law implies du or dE that is equal to du, that's the internal change in internal energy, that is equal to dq minus dw, okay, because it's given that it's the process for the system at fixed volume, okay. So that means dw that is equal to pdv, and hence that is equal to 0. So therefore this term can be neglected here. So the change in internal energy dE that is equal to dq, and that is further equal to TdS, okay. So we will make use of this definition where dq is equal to TdS, that's by making use of the definition of the second law of thermodynamics, okay. So that means basically we can write TdS that is equal to dE, okay. Now from equation 1, one can easily evaluate dE by dt, that is equal to 2AT plus 4B T cube, or in other words what we can do is we can say that dE that is equal to 2AT plus 4B T cube dt, okay. Now we have to since we have to evaluate the entropy, so ds from this equation, let me call this as 2 and let me call this as 3, okay. So ds that is equal to dE divided by T, okay. So by substituting the value of dE from equation 3, this becomes 2AT plus 4B T cube divided by T, and then dt. Okay, so here ds, that is equal to 2a plus 4b t square dt. Then integrating on both sides, we obtain delta S or S final minus S initial, that is equal to 2at plus 4 by 3 b t cube, and then plus some constant of integration. Okay, let's call that C0, or the S final, that is equal to 2at plus 4 by 3 b t cube plus C0 plus Si. So we can call this again another constant, let's say C1. Okay, so therefore the final expression for the entropy as a function of temperature is S equal to 2at plus 4 by 3 v t cube plus constant some constant C1. Okay, where C1 that depends upon the initial state. Okay, so basically there should be some constant here which will ultimately determine the S as a function of t, so that means because in the none of the option we are having some constant here, so that means the most appropriate match here is 2at plus 4 by 3 bt cube. It's option C, that is correct here. So let's take a look at the next problem. The statement is, consider the electrons in graphene, okay, which is a planar monatomic layer of carbon atom. So it's a planar monatomic layers mean it's a two-dimensional system. Okay, so graphene, it's a two-dimensional system. If the dispersion relation of the electron is taken to be, so the dispersion relationship of the electron inside graphene, it's a linear. Okay, so that is Ek, that is equal to Ck, where K is the Bay vector and C is the constant and K is the Bay vector. Okay, then the Fermi energy EF depends on the number density of electrons. Okay, so that means for the given information, C it's a constant and K is a Bay vector. So we are supposed to determine how the Fermi energy EF it is a function of the number density. So remember that because it's a two-dimensional system, so here the number density is given by the total number of electrons in the system divided by the area of the system. Okay, because of the two-dimensional system. Okay, so let's call this the given equation as equation number 1 here, and further note that the relationship between the momentum and the Bay vector, that is given by equation P is equal to h cut k, which implies that K can be written as P upon h cut. Okay, so therefore Ek in terms of P, Ek becomes Ek, that is equal to Cp upon h cut. Okay, let's call this as equation 2. Okay, now the density of states in two dimension. So the density of states in two dimension, so this expression you have to remember. Okay, so density of states in two dimension in energy range from E to E plus dE, that is given by GE dE, and that is equal to basically Gp dP. So it doesn't matter whether you are talking about the momentum space or the in terms of energy, the total number of what you can say is the density of states, the number that will be identical. Okay, and that is given by A upon h square 2 pi p dP. That's the general expression for the density of states in two dimension. Okay, in terms of momentum. Okay, so now what we are going to do is we will replace P with we will write P in terms of energy, then accordingly we will obtain expression for the density of states in terms of energy. So A by h square as it is, multiply by 2 pi, and now P is equal to what? P is equal to, from this relationship, P is equal to E h cut by C. From this, if you just take a look at this equation, so I am going to replace this with h cut E upon C, and then 2 pi p d, not dx, it should be dp, sorry. Okay, so because P is equal to h cut E by C. So this implies dP is equal to h cut by C dE. So I will replace here dE with h cut by C dE. Okay, where A is the area. Okay, so therefore the density of states in terms of energy, they become GE dE. So after rearranging all the terms, it becomes A upon h square 2 pi h cut by C its square E dE. That's the expression for the density of states. Okay, so let me call this equation as equation 3. Okay, so now further taking into account the spin degeneracy also, the spin degeneracy, so that means the spin degeneracy is given by Gs, that is equal to 2 into s plus 1. So because spin, it's a spin half particle, electron, it's a spin half particle, so s is equal to 1 by 2, so the spin degeneracy factor will be 2. Okay, so the total number of electrons in this system at absolute 0 is given by the total number of electrons is given by n, that is equal to 0 to EF. So we need to simply integrate only up to EF. At absolute 0, you can say at absolute 0, at T is equal to 0 Kelvin, all the electron will be confined up to the Fermi energy. Okay, so this is the product of the Fermi-Dirac probability distribution function, which I am writing here as Fe, and multiply by the density of state Ge dE. Okay, and here when we take into account the spin degeneracy also, okay, so the GEDE, that the factor of 2 will be automatically taken into account. So basically we need to multiply equation 3 with the factor of 2 also to take into account the spin degeneracy. Okay, so and further by making a note that the property of this Fermi-Dirac distribution function, so let me call this as equation 4. The property of this function are such that I'm talking about the this function, it is the Fermi-Dirac probability distribution function. Okay, so let me insert another page here. Okay, the properties of this function are, the probability distribution functions are, it is given by Fe, okay, that is equal to 1 upon 1 plus exponential E minus EF upon kVt for the fermion, where kV is the Boltzmann constant. Okay, so it's plotted at absolute 0. It behaves something like this. This is f of E, and here along the x direction it is the energy E, and this is the energy value EF. Okay, so for energy for E less than equal to EF, okay, the value of Fe, this is equal to unity, and for energy E greater than EF, f of E, this is equal to 0. So this is basically the property of this probability distribution function. So we will make use of this fact here, and if you just take a look at the equation that I wrote in the previous page here, so n is equal to Fe. It's because we are simply integrating this equation only up to EF, okay, and the integration beyond the EF, that will simply lead to 0. So that's why I haven't written here plus another term ranging from EF to infinity, because then Fe will become equal to 0, because here we are also supposed to write something like the FeGEDE. So because Fe is equal to 0, so this integral will vanish beyond EF value. Okay, so therefore the total number of electrons, they are given by the expression n, that is equal to 0 to EF. Now 0 to EF, Fe is equal to 1, so that's why I am writing here 1, and then multiply it by GEDE, which is equal to 2 times, this is the degeneracy factor Gs, okay, and then multiply by the the density of states, which is 2 pi a upon h square multiply by h cut by c its square e dE. Okay, and after integration we will be left with, this will be equal to 4 pi a upon h square into h cut by c its square, and then the integration will yields us ef square by 2. Okay, so that means from this equation I can write rho, that is equal to n by a, and that is equal to 4 pi by h square into h cut by c square ef square by 2. This can be, after the cancellation of the terms, this can be written as 1 upon 2 pi c square ef square. So that means rho it's proportional to ef square, so which indicates that the Fermi energy it's proportional to the rho power 1 by 2. Okay, so therefore here the correct option is A. A is correct.